I am here to relate the accomplishments of a small segment of that total which contributed directly to the landing mission. It is that portion which was responsible for the computer in the guidance and navigation system. In my opinion, this was one of the most exciting and challenging applications of a digital computer yet devised. Therefore, it is quite fitting to discuss this computer at the inaugural of this computer museum. Very briefly, in order to set the stage for this presentation, I intend to provide some historic background of developments in the computer industry that influenced the design of the Apollo computer. I will also describe some of the major requirements of the mission to show their influence. The actual development processes and products may appear to have involved considerable floundering around before narrowing into the final product. To those involved during the development, however, is quite orderly, and I guess most will conclude quite successful. After the movie, I will provide a few war stories related to the missions that illustrate some of the problems and relate the results back to a more normal world of computing. So if we can try the first slide, I guess some lights have to go out. This is the slide of the Apollo computer on the left and what was called the DSKY, the display and control, on the right. And very briefly, some of the characteristics which I'll be talking more about later. It was a 15-bit machine, 11.7 microseconds memory cycle time. It had 2,000 words of erasable memory and 36,000 words of read-only memory. The machine instructions, the numbers put here, don't quite agree with what you will see later. I don't know why they were put on this slide. As you see, it was made in '69. There were interrupts, and double precision operations, and a great deal of input-output, which we'll see more about later. As you can see, any good microprocessor can do this job, so what was the problem? Well, unfortunately, in the early 60s, there were no microprocessors. The so-called mini computer was just evolving. There was essentially nothing suitable for the Apollo mission. During the presentation, I will be using some jargon of the trade that may be obsolete. I do not have time to explain the meanings in every case, so I apologize to those who are not familiar with these terms. Most of the technologies that were used in the Apollo computer were available or just emerging from research and development efforts. No major breakthroughs were necessary. The design was mainly a task of fitting the pieces together in order to meet the requirements of the mission for computational capacity and miniaturization. In order to relate the various technologies with the computers that are probably common to people today, I have this slide. So the 50s are crossed here, and for memories there were relays, drums, delay lines, tape core, ferrite cores coming in the late 50s. And then integrated circuit type components in the 60s. For logic, there are also relays, vacuum tubes, diodes, transistors in the middle 50s, then core transistor logic later on, and then integrated circuits in the 60s. And for interconnections, there were printed circuit boards starting early in the 50s, multi-layer boards in the middle 50s, and then welded cordwood construction and wire wrap, which was used in the Apollo computer in the early 60s. Then above the line are the computers that these various technologies contributed to. There's the old-fashioned ones here, which don't matter too much, but Whirlwind was probably the first attempt to build a real-time digital computer. It was at MIT. Then the various IBM series for the large commercial machines out to the 360 here. Then off to the right, starting with the TX0, are the mini-computer branch, which goes to the PDP-1, PDP-8, and PDP-11 by the early 70s. As you might notice here, I sort of neglected other mini-computers, and I think the reason is probably obvious. Although these were the pioneers, so it's worthwhile to have them on the chart. Then for the aerospace branch over here on the left, back in the middle 50s, there was a machine called a Medida and Verdan. There was also a Bell Labs machine, I think it was called Tridac. back in the same period of time, all transistorized. Most of them, however, were using drum memories. Then the Polaris branch, which the Draper work in here, and further out over here were the Titan missile and the Minuteman missile. The IBM Saturn computer, then the 4Pi machine, and then the AP101 it's called, which is on board the shuttle, which is out here in the early 70s. The architectures of these computers varied significantly. Many were serial, that is, logic operation 1 bit at a time, versus the whole word used in the Apollo and very common today. The large commercial machines were all whole word. The mini-computer branch had shorter word lengths, fewer instructions, and smaller memories than the commercial machines. The aerospace branch, the drive was to miniaturization, therefore many of the computers were serial. Most of the earlier ones used drum memories and were designed for specific real-time control applications rather than general-purpose computation. They were significantly slower than the commercial machines and much smaller. It was this aerospace branch which provided the motivation to miniaturize and develop the semiconductor products which are common today. The branch including the Polaris, Poseidon, and Apollo computers are those for which the MIT Instrumentation Lab, now called Charles Stark Draper Lab, has had the design responsibility. You might ask how the Charles Stark Draper Lab became interested in the design of digital computers. The laboratory's interest had been development of inertial systems and instruments. The lab was developing inertial navigation techniques for airplanes and missiles. The answer to the question is more accuracy is needed and easily obtainable in the analog computation. Digital computation would provide this, as well as more flexibility and stability in the computations. The lab's first significant venture into the field of digital computing came in the Polaris program. The Polaris was a very small ballistic missile launched from a submarine. Inertial guidance was necessary. The guidance computer proposed was a special purpose digital computer designed to solve the specific equations required for the guidance and control system. Now this may be too much detail, but the equations required here are these. For ballistic missile type guidance and control, there's what's called a velocity to be gain vector, which if you could add that velocity to the missile at any instant in time, it could free fall into the target. That VG vector satisfies the differential equation shown at the top here. Then steering is accomplished by computing what's called the cross product between the vector VG and the measured acceleration AT in this equation. And you take the y and z components of this cross product and they become the pitch and yaw rates. That's these two equations here. These two equations will force VGZ and VGY to 0 by controlling the pitch and yaw of the missile. Then when the VGX goes to 0, thrust is terminated and the missile will free fall into the target. This guidance and control technique was originally developed for analog computation but the Navy recognized the need for increased accuracy and decided to use digital techniques in the Polaris program. So to convert those equations into something more suitable for digital, we have these difference equations. So the differential equation before now becomes a difference equation with delta VG now, and delta V, which is the increments of velocity, and this matrix multiplication of Q, VG, delta T. And these are the equations written out for the X, Y, and Z components. We can skip over those rather rapidly, I think. The control equation is still the cross product yet, but the incremental version of it, you get an output of increments of pitch and increments of yaw. And again, when the VGs go to 0, the thrust is terminated. Now, a simple implementation of that kind of equation can be accomplished with a digital differential analyzer. And the DDA was a fairly well-known technique being applied to control systems at that time. It was easy to understand because of the similarity to analog computation. The implementation, therefore, it was natural to use this technology. In this slide, I try to explain what the DDA does. With increment of y, each pulse gets added into this register, which is equivalent to the integration for the variable y. And then each time an increment of x comes, y is added to r here, and as is obvious, if you continue adding it to it, you'll get overflows from this register, and those overflows, increments, are proportional to y delta x. So in effect, this is a multiplication, and the lower part is an integration. The memory registers were magnetic core shift registers, and the logic was diode, transistor, NOR gates. In 1959, the first version of this system flew in a Polaris missile. This is the first guided flight of a ballistic missile flown with an onboard digital computer providing the guidance and control computation. Computers packaged similar to this were used operational into the mid-60s. This computer was about 4/10 of a cubic foot, weighed 26 pounds, and consumed 80 watts. But even before this first guided flight, we were exploring designs which would reduce the size and improve the maintainability of the system. The new design, eventually designated Mark II, repeated the architecture and logic design with improvements in circuits and packaging. Silicon planar transistors were used to replace the germanium junction transistors of the earlier version. Subassemblies were soldered, which were soldered and mounted on printed cards in the Mark I, shown here, were repackaged into pluggable modules utilizing all welded cordwood construction with Malco pin connectors for insertion in wire wrap back panels. Each module was potted in a metal frame. The logic, the schematic is shown here on the right, and it's at least the subassembly in a welded cordwood construction is shown on the left. These are the transistors, two of them here for these two transistors. Then the various resistors and diodes are with welded interconnections. These little modules were glued together, shown across here, and prepared to mount in a header. The next slide shows this completed module prior to potting. A welded matrix which interconnects the logic and actually makes the function of the logic is shown here. It's on each side of the module. Then the final construction of, this is the first computer now of this type. As you see, it's November 1961 at this point, is shown here. The logic is in the center here. There's on the outside edge here is an interface module, a clock module, and over here is the memories. There's two of them in the memory driver. The next slide here is the characteristics of that machine now. As I've mentioned, it's a wired program DDA and serial computation. It had only 12 words of memory, 17 bits, had magnetic core shift register, had 512 3-input NOR gates for the logic. The I/O was incremental data transfer, except for initial conditions, which are read in from fire control was whole word. You see the clock rate was rather slow for today's standards, and this computer then is 1/10 of a cubic foot, 12 pounds, and 40 watts. And that provided the background now for the lab's venture into Apollo. In August 1981, when NASA contracted the laboratory for development of the Apollo Guidance, Navigation, and Control System, the mission and its hardware was defined in only very broad terms. For the computer, a general-purpose digital computer had been assumed to be required in order to handle all the data and computations that were thought to be necessary. In addition, an arrangement of display and controls would be necessary for the astronaut to operate the guidance and control system. Initially, the mission plan required assembly of a large spacecraft in Earth orbit. This spacecraft would carry the 3 astronauts to the moon, land them in the command module on the surface of the moon, and then boost off for the return to the Earth. What was an alternate mission configuration was the final one selected in June of 1962, but in the meantime, we had already started designing the computer for this first mission. The 2 mission approaches probably made little difference in the computational requirements. However, the change in the mission did provide justification for very necessary computer redesign from the Block 1 to the Block 2, which came later. The actual mission, which eventually flew, looked something like this. The boost phase was the Saturn system and had its own internal guidance system to put the command and service module, which is shown here, out in translunar trajectory. So at this point is where the Apollo guidance and navigation system, the thing I'm discussing today, takes over to guide the mission to the moon. At this point, maybe I should try to define what navigation, guidance, and control means. I'm a little nervous here with Doc Draper sitting in the audience because I'm not sure I'll get it right. But in effect, navigation is the same as navigating here on the Earth, where you might take a star sighting with the sextant. That information gets put into the computer, and from that the computer computes what's called the state vector, which is the position and velocity of the missile at any point of time. And then it'll continue to update that as time goes on. So that's navigation. Then anytime there's thrusting, as shown in this point here and up here, there's thrusting. Over here, there's thrusting. That part is the guidance and control. The computer must orient the missile such that the change in velocity will cause the state vector to be updated so that it again will free fall to the targeted point. The same type of phenomena that was talked about in the Polaris system. And while it's thrusting, the guidance system must control the attitude of the vehicle and of course control the magnitude of the thrust in case of the LEM at least, and the direction of the thrust in case of the command and service module in this part. A separate guidance system with identical computer provided control of the lunar module through the descent, which is this part right here is the part that descends to the surface of the moon. So the descent here and then the reascent and orbit. The command module itself, which is this part of the vehicle, stays in orbit while this part lands. So a separate system was on board the LEM. Now to show the configuration within a spacecraft, this is the command module with the astronaut standing in the lower equipment bay where a disky is mounted here. The computer is mounted there. The inertial measurement unit, which is used to measure the acceleration and keep the angle of the spacecraft with respect to inertial coordinates, is mounted in behind the panel there. And then there's another disky that's mounted on the main panel right there where the astronaut's fingers are. In the LEM, the astronauts are standing in the position here, and the computer is mounted behind. Again, this is identical computer, as you can see. The disky, also identical, is mounted down between the two astronauts where it's visible. Identical IMU, landing radar, and some other displays, and then there's a rendezvous radar, which those items make up essentially the information sensors and the computation. In the LEM, as the mission developed from the early concept to these final configurations, there were several areas which applied pressure on the computer design. Initially, it was not hard to recognize that very reliable computer with significant computational capacity and speed was necessary. Also, almost as obvious was the necessity for a very limited size, weight, and power consumption. When the program started, that was about the only requirement. If we knew then what we learned later, or if we had a complete set of specifications as might be expected in today's environment, we would probably have concluded there was no solution to with the technology in the early 60s. Fortunately, the computer designers were more or less free to provide the maximum capacity within a reasonable size and weight power. A location in the spacecraft, which I've just described here, and an estimate of volume, weight, and power were among the first requirements established. Pressure for increased computing capacity and speed developed later as the system analysts gained a better understanding of the computational load. Establishing the interface requirements was a monumental task. The Astronaut Interface was one of these. Computers were not considered user-friendly. Heated debates arose over the nature of the computer displays. One faction argued that meters and dials were necessary. The astronauts were usually on this side. The pressure to go digital won most of the arguments because of the greater flexibility obtained in the limited area of the control panel. As the requirements for the LEM were being firmed up in late 1963, NASA made the decision to use identical guidance computers in both command module and LEM, as I've just described. Joe Shea, who is now Senior Vice President of Raytheon, and I guess he's here in the audience, as Gordon Bell mentioned, was Apollo program manager at that time. He was instrumental in that significant decision, as well as the decision to impose common interface control documents on both vehicles. These decisions may have been painful, but they simplified life for the computer designers. A rather interesting experience in the early manned orbital missions, this is not Apollo now, it was before Apollo, had a far-reaching impact on the mechanical design of the computers and the other hardware. NASA learned that the human animal, when confined in a spacecraft for a week or so, was not as clean as you might expect from observations on the Earth. As a result, all electrical connections and metallic surfaces had to be corrosive resistant. In the computer, which was designed to have pluggable modules, had to be hermetically sealed. This addition to the requirements in 1963 provided another justification for momentum, which was building to support a Block II design. The requirement for reliability was a heavy cloud that hung over the program from beginning to end. It was known that computers were susceptible to intermittent failures, electromagnetic interference, and of course hard failures of components, interconnections, and connectors. Also, even if the computer was reliable, how would one establish confidence in it? NASA had planned to utilize industrial support contractors to augment our engineering team at the laboratory to produce these systems. This followed the successful pattern used in the development of the Polaris guidance system. After competitive bidding processes in the spring of 1962, NASA selected 3 contractors: General Motors AC Spark Plug Division for the inertial system and the system integration, Raytheon Sudbury Division for the computer and computer test equipment, Colesman Instrument for the optical systems. North American Aviation had been selected for the command and service module in November 1961, just shortly after we were on the program. And Grumman Aircraft was selected for the Lunar excursion module in November 1962. This formed the team under NASA's management, which was responsible for the development of the guidance system. The primary contributors to the computer were the instrumentation laboratory and Raytheon, with the other members of the team mainly responsible for the requirements. The Apollo guidance computer, which I will call AGC at times from here on, is a real-time digital control computer whose conception and development took place in the early part of the 60s. It drew from the packaging technology, experience with fabrication processes, and experience with semiconductors from the Polaris program, which I've just described. The architecture was derived from a laboratory design for a unique space vehicle with a self-contained guidance and navigation capability intended for use in a proposed mission to photograph Mars and return. The computer for this mission was designed to use magnetic core transistor logic because of its low power consumption. The instruction retropore, word length, and the number of erasable memory cells were very limited. Provisions were made, however, for a moderately large amount of fixed memory for instructions and constants. A high-density memory of the read-only type called a rope memory was developed for this purpose. The Mars computer incorporated program interrupt, which is a novel technique of single accesses to memory, that at least a part of it. There was 2 parts to it. One for accommodating inputs, outputs, which accepted increments, and this was for single accesses to memory for trivial processes such as the incrementing and shifting. This process later became known as the memory cycle stealing. The use of the interrupt in its various forms was an important addition to the aerospace field and was the major architectural attribute of the AGC. Another important aspect of the Mars computer, which had evolutionary significance in the Apollo computer, was the use of interpretive programs, that is, a large library of subroutines, which perform various high-level arithmetic and language operations. When the Apollo program started in 1961, the first prototype computer developed for the Apollo guidance system incorporated the rope memory, core transistor logic, and the same general architecture relating to interrupt, 16-bit word length, instruction repertoire, and so forth of the Mars computer development. This had a rather limited erasable memory, 512 words. It had 1,000 words of read-only memory. No, wait a minute, I made a mistake there. It had 4,000 words of read-only memory. So 512 words erasable, 4,000 words of read-only. It was soon upgraded to 1,000 words of erasable and 12,000 words of read-only memory. During the evolution between the Mars computer and the descendants, the hardware technology available to the aerospace computer designers was developing rapidly. Mention was already made of the coincident current magnetic core memory. The erasable memory design followed the commercial developments of lithium ferrite cores with low enough temperature coefficients to be practical in the broad temperature range applications. Another important line of evolution was the semiconductor technologies, as shown in this slide. It was the early 50s. We had the germanium junction transistors, which were used in the Polaris program. Then silicon planar transistors came in 1959, followed very closely by silicon planar integrated circuits. Both TI and Fairchild were working in this area in 59. Then micrologic, which was the form used for Apollo, which I'll describe later. 1961, this was a Fairchild development. Then, according to the history books, the first linear IC was 1964, but as see, I crossed this out and made it 1963 because there's a custom design of the Apollo computer, which I'll show in a moment, which was 1963. Then in 68, there were MOS memory chips and microprocessors in 61, various types. While integrated circuits were in development by the semiconductor industry, the lab was evaluating the various forms. Now, that was back in probably 1959, late in the 60s. We were buying a few of these at $1,000 a piece. And can you imagine going to your program manager and telling him you had to buy 4,000 of these to build a prototype computer? Well, fortunately, the price came down a little bit before we had to do that. The micrologic version of the Apollo computer was constructed and tested in mid-1962 to discover the problems of the circuits might exhibit when used in large numbers. Reliability, power consumption, noise generation, noise susceptibility were the prime subjects of concern in the use of integrated circuits in the AGC. The performance of these units under evaluation was sufficient to justify their exclusive use in place of the core transistor logic proposed initially for the Apollo logic design. A portion of the erasable memory addressing circuit retained the core transistor logic as a medium for current switching in the memory select logic. Before the decision in the late 1960s to use the integrated circuit logic, however, there were considerable and sometimes heated debates over the advantages and disadvantages of the core transistor logic versus the integrated circuit logic. In hindsight, I believe everybody would conclude the Apollo program made the correct choice. However, the choice was far from obvious in 1962. The first integrated circuit version guidance computer emerged in 1963 as AGC4 with integrated circuit logic. It's shown here, and you see the task from this point on is to compress that down to something you saw earlier, which is about a cubic foot. Here the rope memory contained 12,000 words, but this figure was shortly upgraded again to 24,000 words, made possible by designing the rope modules with the eventual expansion in mind. No particular mission-related need for this expansion had been identified, other than an uneasiness about the possible insufficiency of the 12,000 words. Within another year, when the first mission program requirements had been conceived and documented, There was increasing concern about the possible insufficiency of even 24,000 words of memory, which prompted further expansion of the computer memory by the mid-1964 to the 36,000 for which the Block 2 design used. Both the fixed and erasable memories was operated at approximately 12 microsecond memory cycle time, which is the time interval between the erasable accesses. This is quite leisurable for the erasable memory and allowed the content modifications between reading and writing, such as incrementing and shifting functions that were needed for the memory cycle stealing operations. The rote memory was inherently slow and was operating a good deal less leisurely. The slide shows some of the early engineering test equipment off to the left there, and a display and keyboard on the right, right in here and this here. The initial designs shown here used electroluminescent numeric displays. A keyboard was incorporated along with the display to allow the entry of data and codes for commands. The unit acquired the designation DISCI for display and keyboard. This AGC breadboard used approximately 4,000 micrologic gates in an 8-leaded TO5 type package. By 1962, micrologic components were available from several sources and soon became available in the smaller TO47 type package, which was necessary to reduce the size of the computer to a flight configuration. The circuits and functional characteristics designed into this breadboard became the baseline design for the first production version of the Block 1 computer. Now, take a better look at what the micrologic looked like. It was RTL logic gates. The TO47 package that I mentioned here is here, which went into Block 1, and this is the logic gate, a 3-input NOR gate. By Block 2, we had 2 gates on one chip now, again, still the 3-input NOR gates. And they were mounted in flat packages, which is shown here. Now, to see what the chips look like, this is a very early slide of a micrologic NOR gate. It's the 3-input NOR gate, the type used in Block 1. I think this is a Fairchild chip, although I'm not certain. Then the Block 2 gate, this is a Philco chip. By the production phase of the Apollo computer, Philco was just about the only source. Other sources have attempted to make them, but were not quite successful in meeting the requirements. Here, to try to point out, again, if you can see, the 3 transistors are right there. These little lines are the resistors that in the collectors and bases that you see here. And of course, these are the bonds to the outside world. In 1962, we procured several thousand units of single gate version at approximately $100 a piece. By 1963, we were ordering in quantities of 10,000 units at $25 a piece. Between 65 and 67, when the program was in full production, the price of the dual gate, shown here, in the flat package had dropped to under $10 a piece. As I indicated earlier, one other integrated circuit was introduced in the Apollo computer design. It was a differential amplifier for sensing the memory outputs. And this is the schematic of that circuit. And the dotted lines there is what became the integrated circuit. It was developed especially for the guidance computer, since a differential amplifier capable of memory sensing was not available. The sense amplifier contained the equivalent of 6 NPN bipolar transistors and 8 resistors. We developed several sources for this chip. This is one of the versions shown in this next slide. I guess you can't see that very well. In order to date that picture was taken at the laboratory in January 1964, so obviously these were developed in '63. Such units were preferred over the discrete component sense amplifiers, not only for their small size, but also the close match of characteristics and tracking between components in the differential stage. It was developed as a custom design for the laboratory in 1963. The next significant step in the development of the Apollo computer was the mechanical design necessary to reduce the volume of the breadboard shown previously to the size more acceptable to the spacecraft. Approximately 1 cubic foot had been allocated in the command module. This is the first mechanical prototype. It was operating in the spring of 1964. It utilized the wire wrap and modular welded cordwood construction, which had been reduced to practice for the Polaris program. It was designed to have pluggable trays. As you see here, this is a tray, 2 trays here, and a connector to the outside world would plug into a backplane wiring there. There would be 2 here, and then there's room for spare trays here. Various configurations. Well, these spare trays were assuming we would have to have onboard repair in flight. Various configurations were studied which allowed in-flight repair and even dual operating computers. The plans for redundant hardware configurations reflect the lack of confidence in the reliability of the computer at that time. By this point in the development, there were many pressures building for a Block 2 design. The strongest came from the conclusion that the Block 1 did not have the computational and interface capacity for the Lunar excursion mission in the Lunar excursion module. The Block 1 design had demonstrated the approach, and the designers knew many improvements could be made without increasing size, weight, and power. I have a slide here which I guess those in the front at least can see that compares the Block 1 to the Block 2. I've already mentioned it's an increase in the size of the memory from 24,000 words to 36,000 for the read-only memory, and 1,000 words to 2,000 in the erasable memory. Considerable increase in the number of instructions. A significant increase in the number of interface circuits from 143 to 227. And then here's an increase in speed. For example, the multiplication time went from 117 microseconds to 46 microseconds. And then there were some double precision operations put in, which were subroutines in Block 1. So the Block 1 took about 4,100 logic gates, that's the single gate, and the Block 2 used 5,600 logic gates, which are 2,800 packages. And as you see, the size went down from 1.2 cubic feet down to 0.9 cubic feet. The weight went down and the power went down in this process. Even though the decision was made in the spring of 1964 to go to the Block 2 design for the lunar mission, the Block 1 had to be completed and flight models manufactured to support the flight testing schedule. And we see here that, whoops, what did I do? There. This is the flight version of the Block 1 system. And it flew in 3 missions, the first in 1966. These missions were long-range ballistic missile type trajectories. The Block 2 design was to result in a common computer for both command module and the LEM guidance systems, as I have mentioned. Also a common diski for the 2 locations in the command module and the 1 location in the LEM. In addition, the mechanical design requirements included hermetic seal of both computer and diski. Mechanical parts would be made of magnesium in place of aluminum to save weight, and the finish would be corrosive resistant. In-flight repair had to be abandoned. Now, with this as the background, I would like to concentrate on the final product, especially its architecture. The architecture of the computer remained very similar to the Block 1. The computer has 3 principal sections: a memory to the right here, the central processor, and the control section over on the left. The memory section is divided into 2 portions, the fixed and the erasable. The fixed, or the read-only portion, was 36,000 words, and the erasable was 2,000 words. The central processor section included the arithmetic unit, the instruction decoder at the bottom, interrupt control at the top, and a group of central registers made up of integrated circuit logic. Then memory address registers, a memory buffer register, which had the parity circuits on it. Then the timing and the control. The clock in the computer was the prime source of time throughout the spacecraft. So it had to be good to a few parts per million. Then the various circuits to control the sequencing and timing of the processor. The data and instruction words in the memory are 15 bits plus parity. Data is represented as a 14-bit binary word plus the sign bit. Double precision operations were permitted to or provided to supply 28-bit computations. The instruction word contains the address and operation codes for the computer operation. The primary 15-bit word is here. There was an extend bit provided, shown over there on the left. And then there was multiple use of the bits through the center here. As you see, the opcode used these bits, as well as the addresses for various parts. The memory address field was extended by organizing the memory in banks, and a memory bank register provided 3 extra bits to address the 2,000 words of erasable memory, and 5 extra bits to address the 36,000 words of fixed memory, which would in fact be tacked on over in here on these address. Now, the instructions provided here, I doubt if many of you can see these either, but there were sequence changing up at the top here. There's the memory cycle time shown here, and whether they, as a result of the sharing of those bits in the middle, you had to restrict some of these instructions to certain parts of the memory. So over here on the right defines what part of the memory those instructions are applicable. And the instructions marked with the asterisks required the extend operation to precede the actual sequence. Then these are arithmetic operations and then some input-output operations. There were also a number of involuntary operations, as I've mentioned previously, that were not under the programmer's control, that can interrupt the normal sequence of instructions. First, counter interrupts may take place between any 2 instructions and consume 1 memory cycle time to update contents of any of the 29 counter registers. Incrementing and shifting are operations of this type. Second, program interrupts occur between 2 instructions if no interrupt is in process, and transfer program control to a predetermined address in fixed memory. There were 11 of these. The interrupts are generated from the overflow of timing counters or in response to interfaces such as keyboard, uplink, downlink, and others. Also a restart generated by hardware alarms. The instruction codes, both voluntary and involuntary, were designed to provide flexibility for types of computation control functions needed in the Apollo mission. These were augmented by an elaborate set of software interpretive instructions, which were considerably slower but provided double precision trigonometric and vector operations. The instructions were chosen with consideration for the type of computations required in the computer. There was no systematic evaluation of the instruction set. And after the fact evaluation was conducted from a tabulation of the instruction usage during a portion of the lunar landing mission. A dynamic count of instruction usage was obtained from an all-digital simulation of 10 seconds of power descent, and a static count was obtained from the assembly listing. The dynamic count is plotted as a histogram of memory cycles for each instruction, arranged in the order of decreasing count. So the memory cycles on the left-hand side, and these are the various instructions arranged in the order of decreasing count. The shaded areas are the memory cycles for the extend operation preceding the extended operations. So all of these with the shaded areas on top were instead extended instructions. From this analysis, it can be concluded that instructions which required the extend bit to be set are mostly those with lower dynamic and static count. thus minimizing the time and memory capacity wasted by the extend operations. The involuntary incrementing and shifting instructions that process much of the I/O data were also tabulated. These consumed a significant fraction of the computer time. In total, the information transfer between the computer and its environment uses a substantial proportion of the computer's hardware and computational time. The GNNC block diagram illustrates this. Back in the good old days, Doc Draper used to call the digital computer in his system the junction box. This is a very descriptive term as shown on this slide, even if it doesn't stroke the ego of the computer designers. As you see, you probably can't read any of these words, but the various inputs come in and provide the outputs. So all the computer is doing here is connecting inputs to outputs and doing a little arithmetic on the side. Incremental information transfer was adopted as a means of analog data transmissions in order to maintain high precision with relatively simple techniques of A to D and D to A conversion. For example, incremental transfer was used for angle commands from the computer to the gyros. You can't see those, but they're off up here as the inertial measurement unit. They were also used for thrust control, which is, I can't read them here, so I don't know how you could. Right up here, ascent engine and descent engine. Now, certain displays in the spacecraft. The gyro torquing is an example where a pulse of torquing current of duration delta t, which you see right here, generates a change in angle of delta theta in the gyro. So delta theta is proportional to k delta t. To generate the interval delta t, a number n is loaded into a counter in the computer up here. And then the start bit is set, which allows the counter to count down until it goes to 0, and then the count is stopped. So you send out a number of pulses, n, and comes out here and sets this flip-flop, which generates that pulse length right there. And then the current drive electronics controls the amplitude, so the integral of this area determines the angle which the gyro turns. I sort of hope Dave Scott's in the audience. I don't know for sure, but I'll assume he is at this point. The DSKY is another illustration of the interface design. Since the DSKY was the human interface with the computer, its design was quite challenging. Computers, as I've mentioned, were not user-friendly. There were debates on the role of the astronaut in the operation of the system, and since Dave Scott is here, he should be able to support the astronaut position. This slide illustrates one extreme, and it is probably the one preferred by the computer designers. But again, this slide illustrates the other extreme. It wasn't hard to decide that neither of these two extremes were applicable. The astronauts would have a significant role in the operation of the system, and a suitable interface had to be designed. Heated debates arose over the nature of the displays. One faction argued that meters and dials were necessary. The astronauts were usually on that side. Time must be displayed in seconds, minutes, and hours, using the rotating hands of a normal clock. The display of velocities and altitudes should also be dials. Doesn't this sound strange with digital watches, clocks, hand calculators, and other digital displays we have today? The pressure to go digital won most of the arguments as a result of the greater flexibility obtained in the limited area of the control panel. In the LEM, altitude and altitude rate remained an analog readout supplied by the computer. These parameters were critical to the lunar landing, as you might expect. When the debates narrowed down to something closer to the final product, the issues revolved around color, size, intensity of the lights. As you can see here, the numeric lights on this side and then some status lights on that side. For the keyboard, pressure to actuate, size, and placement of the keys was to be determined. We attempted to use standard keyboard format that the telephone company was establishing for numerics, but it came out inverted with respect to the push-button phones of today. I don't know whether you recognize that or not, but this is inverted with respect to the push buttons. Dave Scott was in the middle of these debates to resolve the requirements on the DSKY and eventually signed off on the top assembly drawing of the display and keyboard, thus providing final resolution of the debated issues. Functionally, the DSKY was an integral part of the computer, but it was mounted remotely and operated through the discrete interface circuits. And these are the outputs at this point. So this is the computer interface. The principal part of the DSKY display is a set of 3 numeric lights, registers, shown right here. Each register contains 5 decimal digits consisting of segmented electroluminescent lights. 5 decimal digits are used so that computer word of 15 bits can be displayed in either decimal or octal number systems. In addition, there are 3 2-digit numeric displays, 1, 2, 3, that indicate the major program in progress, the verb code and the noun code. The verb-noun format permitted communication in language with syntax similar to that of the spoken language. Examples of verbs were display, monitor, load, and proceed. And examples of nouns were time, gimbal angles, error, indications, and star identification number. Electroluminescent lights were used in the DSKY since they are small, easy to read, and required relatively little power. The lights were driven by 250 volt, 800 hertz from an amplifier in the DSKY with the gain or output amplitude controlled by the spacecraft light intensity control. The display is switched under computer control by miniature latching relays in this group here, whose contacts are used for the decoding logic between the computer's 5-bit binary data and the 7 light segments of each decimal digit in the display. In addition, the latching relays provided memory with no consumption of power following the switching action. The relays are selected and switched using a 15-bit parallel direct coupled interface controlled by channel 10, which would be these circuits here. The relay selection is accomplished by a double-ended selection matrix. 4 of the 15 bits are used to select 1 row out of the 12, and the remaining 11 bits are used to select the 11 latching relays in the selected row. 5 relays are used for each decimal digit. Therefore, the 11 relays control 2 decimal digits and 1 other discrete function, such as the display of polarity or of a decimal number. The keyboard has 19 keys that provide the communication between the operator and the computer. Each keyboard input provides an interrupt such that the computer program does not have to scan these bits for activity. Commands and requests are made in the form of sentences, each with a noun and a verb, such as display velocity or load desired angle. To command the computer, the operator presses the verb. You might be able to see it over here. Key followed by 2 digit keys. This enters then the enter. This enters the desired verb into the computer, where it is stored and also sent back to the DSKY to be displayed in the verb lights. The operator next enters the desired noun in a similar fashion using the noun key, and it is displayed in the noun lights. When the verb and noun are specified, the enter key is depressed, whereupon the computer begins to take the action that has been commanded. When the computer requests action from the operator, a verb and noun are displayed in the lights, and a relay is closed. It causes the verb and noun lights to flash on and off, so as to attract the operator's attention and inform him that the verb and noun are of computer origin. The flashing stops when the operator has completed the requested action. The DSKY also provides status displays, as you see on the left-hand side. These display panel is lighted using redundant filament type bulbs so that white, yellow color codes could be displayed, signifying status and caution signals. Among the status display on the DSKY is the restart light, which is one right about in there. This is one of the outputs of a fairly extensive set of failure detection circuits shown in this slide. Doubt if you can see them here, but these include things like Watchdog timer, Parity fails, interrupt lock if the computer got locked up in some fashion, then voltage fail here if power is lost. The computer had a standby capability, so that would indicate here that this goes into standby. And then the restart would go to the diskey to light that, and through a filter it would go to the main spacecraft warning, so that the astronaut has to take some action in the case of a computer failure. In addition to the hardware restart to the diskey, a software-initiated restart would flash the light. The final output was to the spacecraft main caution and warning panel. This completes the essentials of the computer architecture.